Quantum computing. You hear that phrase and it sounds like something straight out of science fiction, right? It promises to change, well, everything, from medicine to money. But let's be real, how much of that is actually happening and how much is just hype? Today, we're gonna cut through all that noise. We're gonna find the signal and separate the incredible potential from the wishful thinking.
So let's start with the promise, because wow, it is absolutely staggering. You see, quantum computers aren't just a souped-up version of your laptop. No, they're a completely different beast. We're talking about machines with the potential to chew through problems that are just impossible for even the biggest supercomputers we have on the entire planet. I mean, just imagine this. What if you could simulate a molecule with perfect atomic-level accuracy? We could discover brand new drugs or design materials with unbelievable properties, like super efficient batteries or next-gen superconductors. And we wouldn't be doing it over decades of trial and error, but in months, maybe even years. This is probably one of the most real, most exciting promises of this whole new quantum era. And look, this isn't some abstract academic thought experiment. The potential for disruption here is massive. We're talking about finance, logistics, pharma, you name it. So to really get a handle on this revolution, we've got to do one thing first: separate the marketing from the actual mechanics. And that, right there, brings us to the biggest tension in the quantum world today. There's this massive, massive gap between the hype that we all hear about and the actual state of the hardware that's being built in labs as we speak. So to help us unpack all this, we're turning to computer scientist Scott Aaronson. And he's pretty blunt about it. He argues that the whole quantum landscape has basically split into two completely separate worlds. On one side, you've got the hype companies. They're selling a fantastic story to investors, talking about revolutionizing AI and finance. On the other side, you've got the hardware companies. We're talking about places like Google, Quantitunium, and Quera. And these folks are quietly making incredible, tangible progress on the fiendishly difficult physics and engineering problems. So let's zoom in on that progress for a minute, because it is genuinely exciting. Despite all the noise, experts who were once, deeply skeptical are now starting to take these company roadmaps a lot more seriously. And there's one key reason why. This number right here, greater than 99.9%. This is all about reliability. Multiple teams have now managed to make their quantum operations that reliable. And that is a huge deal. Why? Because it's the magic number, the critical threshold you need to build quantum computers that can actually correct their own errors. Something that was once just a theory is slowly but surely becoming an engineering reality. Okay, so we have a better grip on the hardware reality. The dream is getting closer. But what are these machines actually gonna do? What are the real-world problems they're uniquely built to solve? Despite all the crazy headlines you see about AI and finance, Aaronson points out something fascinating. The list of known high-confidence applications, it's been pretty much the same for over 25 years. It really just boils down to these three things: simulating other quantum systems, breaking modern encryption, and maybe offering some modest speedups for certain complex optimization problems. So what does that actually look like in the real world? Well, simulating quantum systems is the big one for science and industry. It could mean designing personalized cancer treatments based on your unique biology, or creating catalysts that literally pull carbon out of the atmosphere. And then there's that second application, breaking encryption. Yeah, that's the one that has governments and security agencies, let's just say they're paying very close attention. And you know what? That cryptographic threat is so massive, it really deserves its own spotlight. Because this isn't some far-off science fiction problem. This is an active threat, right now. Now, this next analogy is, honestly, it's pretty chilling, but it's also incredibly powerful. Back in the 1940s, physicists figured out that an atomic bomb was possible, and they immediately classified their work. Aaronson is warning that we might be walking into a similar moment with quantum code breaking, where the really detailed research on how to do it just stops getting published out in the open. So why the crazy urgency? It all comes down to this one strategy: harvest now, decrypt later. It means that adversaries are already stealing massive amounts of encrypted data. Think about it: national security secrets, valuable corporate research, your personal health data, and they're just storing it. They're making a bet that someday they'll have a quantum computer powerful enough to crack the encryption and read it all like an open book. And this timeline, this really lays out exactly why we can't wait. Your data, our data, is already at risk of being harvested.
And while the experts have this huge range of estimates, anywhere from 5 to 40 years, for when a machine could actually break today's encryption, that doesn't really matter. The clock has already started. Any data that you need to keep secret for the next decade is already vulnerable today. Okay, so what do we do about all this? How do we prepare? The challenges are absolutely real, but guess what? So are the solutions. This isn't about panicking, it's about being proactive. For any organization, really, the path forward breaks down into 3 key steps. First, you've got to build awareness, really understand what's at stake. Second, collaboration is key because no single company or even country can solve this alone. And finally, you have to start preparing for the big migration to new quantum-resistant encryption standards. And look, the good news is this isn't just a theory. It's already happening. Governments and standards bodies are taking this very seriously. Here in the US, the National Institute of Standards and Technology, NIST, has already standardized the first batch of these new algorithms. The global upgrade has already started. Ultimately, this is what it's all about. We have to steer this transition very carefully so we can get all the incredible benefits, those new medicines, those new materials, without triggering a catastrophic breakdown of digital security and the trust that holds it all together.
And that brings us to one last really big thought. We've spent our time talking about what we know quantum computers will be good for. But think about it. The people who built the very first classical computers, they couldn't have possibly imagined the internet or smartphones. And that's the thing. The most exciting, world-changing applications are almost certainly the ones we can't even conceive of yet. What new realities will this technology unlock for all of us?